Hi. So I just finished the homework for 3.2 and I am exhausted. The concept isn't super difficult. I mean, it's regular difficult. The problem is each problem takes a long time because you have to be meticulous. And I got a couple of them wrong and I had to go back and do them over again. So take your time, go slow, write every step down, and that'll help. But good luck. This section introduces the chain rule and then revisits the power rule from last section with some more complicated exercises. Then we put all your new tools together in some even more complicated exercises. Let's start by giving you your new tool, the chain rule. We'll look at it a couple different ways. First, using that ddx notation we've used a little bit so far. If you have a function y in terms of a variable u, and then another function that defines u in terms of a second variable x, then the derivative of y in terms of x, that's dy dx, is equal to the derivative of y in terms of u, dy du, times du dx, which is the derivative of u in terms of x. This version of the chain rule is most useful when looking at applications, so let's do that. All right, here's our first example. Studies show that the average level of certain pollutants in the air is given by L equals 1 plus 0.2x plus 0.001x squared parts per million when the population is x thousand people. It is estimated that t years from now, the population of a certain town will be x equals 100t squared plus 74,000 people. Find the rate of change of the level of pollutants after 6 years. To find the instantaneous rate of change of the level of pollution, we can calculate the derivative of the main function L. But that will give us the rate of change of the pollutants in terms of x, which is the number of people, the population. But we want the rate of change of L with respect to time. Notice the question asks about the rate at 6 years. So we need to use the chain rule since we have x, the population, defined as a function in terms of time t. Using the chain rule, we have dl dt, that is the derivative of L with respect to time, which is what we don't know, which is what we want to figure out. It's equal to dl dx, which we have above, right, times dx dt, which we can calculate. Notice it looks like you're multiplying two fractions, and if you were, those dx terms would cancel out and you'd be left with dl dt. Of course, that's not what's happening, but it's a nice way to remember the structure of the chain rule and to get everything in the right place. All right, replacing dl dx with what we've already found, and dx dt is 200t. Remember, x is 100t squared plus 74, so we differentiate that and we get 200t. All right, so now we have dl dt. We can evaluate it at t equals 6. That's what we want, right? All right, so plugging in t equals 6. Oh no, we still have an x in our function. Oh, but remember, we have a function that tells us what x is in terms of t. Plugging in 6 gives us a population of 3,674 in thousands of people at t equals 6 years. So that gives us a number that we can plug in for x. Okay, and now we have 9,057.6 parts per million. So because it's a positive number, we know that the level of pollutants is increasing at this rate at 6 years. All right. Okay, let's look at another way to define the chain rule using some different notation. If you have a function y that you can think about as a composite of two functions, that is f of g of x, remember that? Then the derivative of y is the derivative of f in terms of g of x times the derivative of g of x. I like to say it's the derivative of the outside times the derivative of the inside. Some people like one way better, some people like the other way better. It really depends on the kind of question you're getting, but I promise, is the exact same rule. To understand better, let's do another example. All right, this is a purely symbolic example. So we have h of x defined as this trinomial cubed. The trinomial is 4x squared minus 7x plus 11. And we're just going to cube that whole thing. So one of the things we could do, right, is we could multiply that trinomial out 3 times, and wouldn't that be a mess? But then differentiating would be easy. We just differentiate each one of those terms of the polynomial. But we can use the chain rule here to do it, so we don't have to do that massive amount of algebra. So to be clear, the outside function here is just f of x is x cubed. We're just cubing something. The inside function is g of x is that trinomial, 4x squared minus 7x plus 11. So try to think of it as f of g of x, okay? So we have an outside and an inside function. This sometimes gives people trouble, but hopefully you can remember how to do that from algebra. All right, so the derivative then of h of x is the derivative of x cubed, which is 3x squared, okay? But it's in terms of g of x, the trinomial. All right, so that's why we have 3 times the trinomial raised to the second power. And then we multiply that times the derivative of the inside g of x, which is 8x minus 7, okay? You can, after this, you can multiply and simplify and stuff, but it doesn't do much after this. Basically, you can distribute that 3 maybe, but this is a totally acceptable answer. We are done. Which brings us to the general power rule. Basically, it's another name for what we just did. It's really just doing the chain rule if, in particular, the outside function is raising the inside function to a power. Okay, so that's exactly what we just did. So if you have your function y is some g of x raised to some power n, what we just had, then its derivative is n times that g of x raised to the n minus 1 power. So there's that power rule, right? Times the derivative of the inside, which is g prime of x. It's really just the chain rule. All right, so I'll put it there, but I mean, we already know it. Okay, so we shouldn't act like we have to learn a whole new thing. Okay, so don't freak out. We really just learned the chain rule in 3.2, which is nice, but the rest of the homework is basically using the chain rule, the power rule, the product and quotient rules, the sum and difference rule, all the rules we've learned so far, all the little shortcuts for differentiation, putting them all together. And it's super fun if you like being meticulous. If you have trouble being meticulous, this will be where you are challenged, okay? Some of these problems take a lot of space on your page, and I encourage you to use all the space and all the time that you need to reduce the number of mistakes. But remember, when you make a mistake, that is a great learning tool so that you don't make that mistake again, okay? So rather than get frustrated, take note of where you made the mistake and then make an effort not to make the same mistake again. Okay, so we'll be practicing these in our Zoom class, and that is it for 3.2. Good luck, and I look forward to seeing you.